Okay, take your attendance as usual. Okay, guys, so let's we start our lesson today. Let me check. Am I recording? Okay. Okay, we will be just continue the quantum physics. We just introduced yesterday. So let's we try to explore more. Okay. Okay, so like yesterday we just introduced with you what is meant by quantum physics. It's like what do you call? We want to. It says it's a microscopic investigation for the energy. Okay. So first we found that under quantum physics they introduced photon. Okay, concept of photon. I think we discussed this. So we are just started to discuss this second controversial experiment, right? The photoelectric emission, I told you. Okay, so we will be discussing this today. Okay, so just skip the few slides. So photon is a packet of energy of a EM radiation. We done this. Then we skip this. Okay, so you have to know what is meant by photoelectric emission. The release of electron from a surface of a metal when EM radiation is incident on its surface. Okay. Then I say this is a controversial experiment which oppose the idea of that light is a wave. Okay. Okay. Why it opposes the outcome, right? So I'll show an animation for this setup later. I'll show. So these are the outcomes, which against the wave idea. Okay, I believe I told you, right? First thing, the first observation, which against the wave idea is that the emission is instantaneous. Okay, the emission is instantaneous. But wave predicted what? The wave idea predicted what? Must have a delay. Must have a delay in release of electron. Okay, I told you like a metal plate. If the electron is bonded with a with energy of let's say 100 eV. If the light shine as an intensity, let's say it releases 5 eV per second. Let's say 5 eV per second. It means the electron have to wait 20 seconds. 100 eV divided by 5 eV per second. So the electron need to wait like 20 seconds to be released from the metal plate. So the emission should have a delay. More lower the intensity, the delay must be more critical. Delay increase. But here, whatever intensity they use, the electron release instantaneously. That's the first one. Okay, second one, the photon emission takes place. It has a certain threshold frequency value. It has a certain threshold frequency. So what is the meaning of that? If you go lower than certain frequency, okay, let me show the animation better. While I teaching this, I go back to the animation. Okay, let me show you the threshold frequency. What is meant by threshold frequency? I just go to the, there is one. This is the setup. This is the photoelectric effect setup. So this is the metal plate. This is the voltage, which at the beginning we keep 0 volt. We never apply any voltage. The voltage, the voltage idea is by millicurrent. I'll come back to that later. Okay, first you see here, I shine a light. You see on top here is intensity, and bottom is the wavelength, different wavelength. So first, let's say I increase the intensity. I increase the intensity. Okay, I increase the intensity. So when I increase the intensity, electron get energy, releases. Okay, and got current. This is the current. The current due to the electron flow into the circuit. So what happened? First thing. So node have intensity. I make it low. Okay. So this is ultraviolet. Ultraviolet is a very low wavelength, 400 nanometer, and a very high frequency. That's a very high frequency. So I put a little intensity. So electron release instantaneously, although it's low intensity. Okay, I got current. Very low intensity. But let's say I increase the violet to blue. I change the color from violet to blue. Blue means high frequency or low frequency, blue color compared to violet. Low frequency, right? So I reduce the frequency, blue. Okay, you see blue. So blue also the electron releases lah. Whatever low intensity also blue releases. Okay. But let's say I put at red. I go and put at red. I put it at red. Okay. Now I shine with the red light. Okay. Red light I shine. I increase the intensity. Very high. Very intense red light. Not even one electron release. Not even one electron is released. Okay. So they reduce the frequency a little. Not even one electron. I go to the orange, still no. I put yellow, no. I put green, still don't have. Yeah, so you see, I put at a 516, got electron release. I put like, what do you call? Shorter, more lower frequency, lower frequency, maybe at yellow, no electron at all release. So that means this experiment found that there is a threshold frequency. Threshold frequency means at certain frequency, higher than that frequency, the electron is released. Lower than frequency, the electron does not release. Although I increase the intensity very high. Okay. But we predicted that energy is depend to intensity. You put a very high intensity, regardless of whatever frequency, the electron should release. Right? You put a low red light also, low frequency also, but you put very high intense, the electron should release. Because the wave idea, the energy is dependent to the amplitude, not frequency, right? Nothing to do with frequency. The energy of a wave is nothing to do with frequency for the wave idea, the wave idea. Okay. Yeah, so this is the second blow. So, so the photoelectric take place. Frequency of the incident radiation above a certain value called threshold frequency. But what wave idea predicted? Wave idea predicted any frequency must release electron. This is your wave idea. This is your wave idea. Okay. And the third one is the last point. The last point. Okay. For a given frequency, the rate of emission of the photoelectron is proportional to intensity. This is emission, sorry. The fourth one, sorry, the fourth one. The emission of electron, whether the not emission takes place depend only whether the frequency of the radiation is used above the threshold for that surface. It does not depend to the intensity of radiation. Yeah. The release of electron looks like nothing to do with intensity. It's something to do with frequency. Okay. Okay. So another two outcome they found, different metals need different threshold frequency. They found, the metal at the left side, the metal here. Okay. The metal here was changed in a different type of metal. The threshold frequency changed. That means for this particular metal, I think 516, right? Yeah. Wavelength of 535 releases electron. Okay. If you use a different metal, depend to the bonding of electron. If stronger bonding, it seems the threshold frequency rises. Okay. Yeah. So for a given, so different metal need a different threshold frequency. Okay, yeah. So these are the three outcomes you have to remember. In exam, they'll ask, what is the three outcomes against the wave theory in photoelectric effect? First, you said the emission is instantaneous. The threshold frequency emission needed a certain threshold frequency. The release of electron is independent of intensity. Okay, so 5 years, nobody unable to explain. So as I told you, Einstein explains this outcome. Whatever idea Einstein put forward, he must explain this outcome. Okay, so what Einstein said, this is what he said the day I show you, right? So Einstein's theory about photoelectric effect, which gave him a Nobel Prize, quite close to 1 million, 1 million, and of course huge recognition. So, so Einstein said, okay, the energy of a wave, energy of a light is in terms of packet, he said. Okay, he said when the light interact with the matter, okay, the energy of a light is looks like it's in a packet. Okay, so he said photon. The idea of Planck photon idea has been brought by Einstein. Okay, so he said the photoelectron interaction and HF is transferred to the electron in the emitter. Okay, so what he said, this formula. Okay, this is the formula he said. You see down here, HF phi half mv squared. Okay, this is what he explained. You see HF. HF is what? The kinetic, the photon energy. Okay, electron get one photon energy, and that photon energy the electron used for two things according to his theory. He said the energy is used to break the bond. The phi is actually energy related to the bond. Okay, to break the bond. This phi got special name we call work function. Okay, work function. It's actually the bonding between the electron and the metal surface. It's called special name work function. If the bonding between the metal and the electron is strong, we say the work function is high. Okay, work function. So whatever photon energy absorbed by the electron is used to use it to overcome the work function. Okay, to break the bond. Then the balance energy, if it has any balance, then it turn to be it gain it as a kinetic energy. Okay, so that's the idea he said. Okay, so yeah, so this is the equation he said, and HF equals to phi plus half mv squared. Okay, so now he add more thing. He said one electron only receive one photon. Okay, so I go back to the whiteboard. Okay, so the metal plate. Okay, the electron is bonded. the energy of the light is say in packet. One electron get one packet. So HF, the electron use it for work function, break the bond. Let's say the bond, let's say for example, let's say the photon energy is 100 10 EV, let's say. Let's say the photon is, so I put a big number. Okay, let's say the electron bonding is 100 EV. Okay, 100 the bonding and the work function is 100 EV. Let's say it's 100 EV. Okay, the energy in one photon, let's say the one, let's say it's a blue light. It's a blue light. Okay, it's a blue light. The photon, one photon of blue light, let's say has an energy of, let's say 150 EV. Okay. So the electron get the HF is how much? 150 EV. Okay, the electron used to break the bond. So the 5 become 100 EV. So the balance turn to become kinetic energy of the particle. So in this case, the electron should come out with a kinetic energy of how much? 50 EV. It should have kinetic energy of 50 EV. Okay, this is the idea you see. Okay, so you say that if the blue light, right? The blue light, you change to violet. If you change the blue light to violet, okay, you change to violet. Okay, if you change to violet, what happened? The photon energy for violet is greater. The violet photon maybe have 200 EV because its frequency is high. So because photon energy is depend to frequency. So the photon, one photon of violet will have 200 EV. When it go and strikes the electron again as usual he use to break the bond, he use 100 EV. Okay, because the bonding is the same one, same metal plate. So, but you get 200 EV from the violet. So how much of kinetic energy will have? It will have 200 EV. Sorry, 100 EV. So kinetic energy of the particle will rise. This is the idea he said. Okay. Now we explain. Let's you see how this explains the outcome. What is the first outcome of the experiment? The release of electron is found to be instantaneous. It's instantaneous. It's instantaneous release. So it explained, right? You see, last time it's a wave idea means the electron is 100 EV means the electron must wait to collect the energy from the wave until it get enough energy, it will release. So the delay happens, right? The prediction, the wave prediction delay should happen. But according to the wave, the theory, what do you call it? The theory by Einstein, why the electron need to wait? You don't need to wait one. Once the light strikes, the electron get immediately one photon, one packet of energy, immediately release. So Einstein able to explain it should be instantaneous. Okay, the electron no need to wait to collect the energy. You just need to get one photon, that's all. One packet of energy get, it will be released immediately. Okay, so that's the first outcome has been explained by, it matches with Einstein's idea. Okay, second idea is what? Second idea is threshold frequency. Threshold frequency. The existence of threshold frequency. Okay. So just now I show you in the animation, right? In the animation. Okay. So you need certain high frequency. You go more than high frequency, the electron will release. You go lower than that, the electron won't release at all, although you rise the intensity. Okay. But now, is it Einstein's idea explains that? Einstein's idea said, yeah, makes sense, right? Let's say the electron bonding is 100 EV. Okay. You send a light of a rate. You send a light of a rate. Okay, rate. Okay, rate as a very low frequency. Okay, so rate. Let's say the photon energy of a rate, let's say, is only 80 EV. One photon rate is 80 EV. Okay, you shine this metal plate, which electron is bonded with 100 EV. You shine this red light. Do you expect the electron to be released? He can't release, right? The bonding is 100 EV. but the photon energy of a ray is only 80 eV. So what will happen? Electron won't release. It can't release. How it can release? Because the packet of energy received, the energy inside one packet is lower than the bonding, not enough to break the bond also. Okay, so red light, you use high intensity also. If you use high intensity means what has been changed? If you use high intensity, if you use high intensity means, the number of photon increases. The number of photon increases. You get more packet of energy available per second reaching the surface. But energy in one photon is very low, 80 eV. So one electron only get one photon. One electron never get two photon. Only one photon. He only can absorb one photon. According to his idea. So therefore, electron won't know at all will release. So his idea explains the existence of threshold frequency. Okay, threshold frequency has been proven. Should have threshold frequency. Okay, that means lower than certain frequency, the electron cannot be released. Why? Because the photon energy is lower than the work function. Okay. And the third factor, you can say it is the release of electron is independent of intensity. Of course, right? You see the red light, you raise the intensity, only the number of photon will be raised, but not even one electron can be released because energy in one packet is very small than the work function. So definitely intensity not affects the release of the electron, not affects the release of the electron. Okay. Yeah. But what intensity does? You rise intensity, what happened? If you rise intensity, what happened? Go to the diagram. You see, the animation. You see, go to the low intensity first, low intensity. See, I put violet lah. Make sure the electron comes out. So you see, the electron is coming out. The electron is coming out. I put the intensity. Tell me, what type of change happen if I rise intensity? What intensity affects what? You see, I go up. I just rise the intensity. Look at the diagram. I rise the intensity. Go to the big one. Okay. So when I rise intensity, what happened? The current increase. The photo current increases. Okay. So intensity increase the photo current. Okay. Why intensity increase the photo current? I put less intensity. You see the photo current at the bottom. You focus on the photo current. I put very high intensity. The reading is 0.136 ampere. I reduce the intensity and see low intensity current drops what? 0.072 ampere. Okay. So why rising intensity? Current change. Current is changing. Why current changing? Because why current changing? Because according to wave idea, sorry, not a wave idea. Okay, if I write, it's going to be shut down. So yeah, why intensity rise? The current increases. What is current? Rate of flow charge is how much of charge passed by in a second, right? Okay. So the current, if you rise the intensity, the number of photons reaching the surface will increase. Okay. Right? Intensity is what? Intensity is power over area, right? You learn in your wave knowledge. Power is what? Energy over time over area. That's your intensity, right? So intensity what? Energy over area time, right? But for quantum physics, energy is what? Energy is in terms of NHF, right? NHF, n number of photon, right? This is the one golden formula for us to visualize why the current is increased when you rise the intensity. You see, look at this equation. When intensity rise, H never change, is constant. Frequency, we fix the frequency lah. The frequency of the maybe the violet light frequency fixed. Area of the surface area is fixed. What happened to the NOT? The focus is NOT. When I increase, when the intensity increase, what happened to the NOT? Increases, right? See the NOT increases. What is NOT? The number of photon, the number of photons strikes the surface area per second increases. You get more photons. You get more photons strikes the surface per second. You get more packet of energy lah. So if we have more photons, let's say the photons increase from 5,000 to let's say 10,000 photons, you will get 10,000 electrons will be released at the same time, you know. So more electrons release, more photon means more electron release. More electron release means more current lah, right? More electron release means more current one. Current is rate of flow of charge, right? Yeah. So the intensity only rise the photocurrent. Okay, it only rises the photocurrent. Okay. So yeah. So this is how Einstein explains the outcome lah, the experiment. Okay, any questions, guys, so far? Okay, no questions. I know it's just a very, what do you call, very new stuff for you, something new, new idea. We will be strengthening lah as usual when we do questions. Okay, we go back to the slide. Okay, so yeah. So yes, read through here. The work function phi is depend on the type of metal. Yeah, the work function is depend to the type of metal. When a photon of threshold F0 is absorbed by the electron released from the surface with zero kinetic energy. Yeah, correct. Let's say what the third point telling is if the HF0 is actually the work function line, the work function. If the bonding of the electron is 100 eV, let's say the bonding of the electron is 100 eV, the photon energy also 100 eV. What will happen to the electron? Electron, is it the electron will release? Yes, the electron will be released, right? Because bonding is 100 eV, the photon energy also 100 eV. So electron will release lah, it will release. But do the electron have a kinetic energy? It won't have kinetic energy, right? Because HF itself is 100, the work function also 100. Kinetic energy, it won't gain kinetic energy. The kinetic energy will be 0. Okay, the kinetic energy will be 0. Okay, yeah. So that's the third point. Okay, now let's continue. So the electron released from the surface with zero kinetic energy. If the photon frequency is F0, F0 called this F0 is called threshold frequency. It's the threshold frequency, the minimum frequency required to release the electron. Okay, so now look at the fourth point. When a photon of frequency is more than F0, is absorbed by an electron, it is released from the surface with a velocity that would range from a smallest to largest. Yeah. Okay, this is another point. I'll get back to the point 4 later. But just for timing, remember, when the photon frequency is higher than threshold frequency, the electrons start to gain kinetic energy. Okay, it'll start to gain kinetic energy. Yeah. Okay. So go back to the whiteboard. I clear this. Okay, so HF equals to work function plus kinetic energy. Okay, the work function we can write as HF0. Okay, plus kinetic energy. What is F0? Is the threshold frequency. Is the threshold frequency. Yeah. What is threshold frequency? The minimum frequency required to release the electron. Okay. Okay. So when Einstein stated this, okay, but he can't get Nobel Prize. You have to prove this one. You have to prove this his idea. Although it explains the outcome, but you need to prove this idea. How we can prove this idea? Scientifically, how you can prove an equation? How you can prove an equation? You must get data. You must do independent, dependent variable. You must plot graph, and you must get a specific, a certain shape of the graph, right? If you use a linear law, you must get a straight line when you plot specific axis, right? Okay. In this case, how Einstein can prove this? Einstein need to measure what he can measure. You need to measure the HF. Okay, H is at the when he explained this theory, the H and the Planck constant is already proven. The Planck constant we know. Okay, so if you want to use a red light, you want to use a red light to shine. Red light frequency we know, so we can find the HF. So Einstein don't have any problem to calculate the HF. HF. So use a red light, HF we can calculate. Okay, but we want to prove this equation. But the bonding, what is the bonding? How much is the electron bonded to the metal? We don't know. The HF naught, we don't know, We don't know how to calculate. We don't know the HF naught. Okay. Then another one, when the electron is released, the kinetic energy the electron possess. Also, Einstein don't know how to find the kinetic energy. He also don't know how to find the kinetic energy. So these two, you cannot find. Okay, you don't know how to find. You just write theory. Okay, so how to prove the equation? Because you don't have data. HF can find, use a red light. So here I can say the independent variable you should select is the frequency. Frequency should be the independent variable. Independent variable frequency. The dependent should be the kinetic energy. Okay. So you did the experiment, right? First is independent. In this case, is a frequency. Dependent should be kinetic energy. But now Einstein got data for frequency. From red light to violet, he got that data. But kinetic energy, you don't know how to find. Okay. If let's say he able to find the kinetic energy, then we can prove this equation. You can prove this equation, right? Use your science law. How you can prove this equation? If you know the frequency, if you know the kinetic energy, how you can prove whether this is correct or wrong? You plot graph, right? What graph you can plot? Suggest a graph. What graph you can plot? You can plot what graph? You can plot. Maybe you can plot. What do you call? Kinetic energy versus frequency. Maybe you can plot kinetic energy versus frequency. So rearrange this formula. Ek equals to what? I rearrange the formula. Ek equals to what? Ek equals to HF minus HF naught. Okay. So yeah. So Ek is your y axis. Your frequency is your x axis. So your gradient plus C. Yeah, makes sense, right? Yeah. So if this formula, Einstein's formula, correct, you plot Ek versus frequency. That means you use a different red light. You use a red light, then use a yellow light. You use orange light. If you know how to calculate the kinetic energy of the electron, if you know, okay, find the kinetic energy of the electron. If you get that data, if you plot y versus x, it must be a straight line. It have to be a straight line. It have to be a straight line. It have to be a straight line where the gradient should represents what? Should represents the Planck constant. Should represent Planck constant. If Einstein's formula is correct. Okay. But now this is not possible because we don't know how to find the kinetic energy. Okay. So then after a few years later, 1905. So 1905, when Einstein wrote this scientific paper, I think about 19, if I'm not mistaken, 1918 or 1916, if I'm not mistaken, I forgot the date. I think 1918. After 13 years later, okay, Millikan said, the the one who discovered the electron, the charge of an electron, he said he can find the kinetic energy. He said he can help Einstein to find kinetic energy. Actually, not to help Einstein, to show that Einstein is wrong. Okay. So now the idea is how Millikan able to find kinetic energy of the electron. Okay, how we can find the kinetic energy of the electron. That's when he said by using this circuit, this animation, this circuit. Okay, he said we can use this circuit. Of course, we have a metal plate and the wire, the current is flowing. He said we can find the kinetic energy of the electron by using a potential, by applying a voltage. Okay, you learned last time, right? You learned last time, right? In your electric field, electric field. Let's say you have a metal plate. You have a metal plate. Okay. Let's say an electron has a kinetic energy of, let's say, 100 eV was moving to the right. Say moving to the right. Moving to the right. Okay. Moving to the right. Let's say you put a micro ammeter, very small current connected. Okay. Micro ammeter. So when the electron is moving to the right, you got current line. You will get current. So according to Millikan said, now the problem is we don't know the kinetic energy of the electron. So Millikan said we can find what kinetic energy the electron traveling by applying a cathode at the opposite plate. Okay, apply a cathode. That means you apply a battery like this. You apply a potential like this. Potential like this, and this potential is varied. Okay, so make the right plate as cathode. Make right plate as cathode. Okay, then what is it? What happened? If this is a cathode, the electron which is moving to the right now facing a problem to move to the right because cathode what? Repelling, right? Repulsive force will happen. So what happened? The electric field does work. The electron have to do work, okay, to overcome this repulsive force. Okay, the work need to be done. Recall back your AS knowledge. What is work done formula in electric field? Work done by electric field. What formula? QV, right? Q times V. Do you remember? The work done by electric field is charge times the potential difference. Okay. So let's say you give a certain small potential difference. Let's say your potential difference you give such that the work done is, let's say, is 20 EV now. Let's say you apply a potential difference such that the work done is 20 EV. Okay. The kinetic energy of the electron is originally 100 EV. When the electron by the time reach the plate here, the electron will possess how much of kinetic energy? How much of kinetic energy? Anybody? You apply a cathode. You want to slow down this electron. The work done by the electric field is 20 EV. Okay. The kinetic energy of the electron originally was 100 EV. But when it goes to in this electric field, he experienced the repulsive force. So it does work. The work done is 20 EV, like a friction, work done against friction. This work done against electric field. So what the electron, the kinetic energy possessed by the electron when it reaches the plate? Anybody? Should be 80 EV, right? Should be 80 EV, right? Because 20 EV used by the electron to overcome to do work against the electric field, which opposing it. Okay. So because the electron reaches here with 80 EV, do you still get current? Yes, you will still get current here. Okay, you will still get current. Okay, but let's say you rise this voltage, you rise the voltage of the electric field, you rise the voltage of the electric field such that the work done by the electric field is exactly 100 EV, exactly 100 EV. What happened to this electron? The electron is just moving forward until, and it by the time reaches the plate, the negative plate, the kinetic energy of the electron become 0. Electron kinetic energy becomes 0, then electron stop moving forward. So at this moment, current become what? Current become, for the first time, current will become 0. So current will become 0. So for the first time, current becomes 0. Okay. When the first time, when they rise the voltage slowly, the minimum voltage where the current for the first time becomes 0. Okay. Then the conclusion is the kinetic energy possessed by the electron is equals to the work done by the electric field. Okay, by the electric field. Okay. So this is what Millikan said. So the kinetic energy, the work done by the electric field is equals to the kinetic energy of the electron. Okay. So from here, Millikan say we can find the kinetic energy. The kinetic energy is, we know EK, we don't know how much, but work done by the electric field we know is QE. It's QE. Q is what? The charge of the electron, elementary charge. V, what V is this? The V they obtain here, the voltage of here. This V give a special name called stopping voltage. It's called stopping voltage. It's called stopping voltage. Stopping voltage. So the V is EVS. So the EVS is said to be kinetic energy of the electron. Okay. So Millikan said, now Einstein stuck because it can't find the kinetic energy. So we can find the kinetic energy by applying a reverse voltage. We just make the electron moving to the right. We make the right electrode become what you call cathode. We slows down the electron. We rise the voltage until the current becomes 0 for the first time. Then the EVS, this voltage multiplied by the E is the kinetic energy of the electron. Okay. So for the animation, see the animation, I show you how Millikan get the stopping voltage. Okay, you see here the voltage down here, the battery, right? You see connected like okay. I reverse voltage lah, reverse voltage. I put, you see, this is 0.6. Electron move faster. I want to slow down. I put a negative voltage. You see, I drag it to the left. I drag it to the left. See, the voltage is -4. -4 means on the right side, it's cathode. You see the electron slows down. I increase some more voltage, you see. The electron slows down. I put very high voltage, you see. The electron all, which are moving to the right, all slows down or moving back. Okay. Because the kinetic energy of the electron is used to do work against the electric field. Okay. Okay, now you see exactly, we find, you see now it's -2 here. I want to find the stopping potential for this plate. Okay, I want to find the kinetic energy, kinetic energy of the electron, which is traveling. So first I slowly reduce it. Okay, now 1.6, I make it negative. I put -0.4, current still 0.036. Means what? The electron still reaching the plate. So we want the voltage where the current for the first time becomes 0. So I have to rise it slowly. -0.4. I raise it little. -0.6. Still go current. You see the electron? Electron slows down, but I think still gets some energy. It reaches the wire. It got current. I reach to -0.8. I see -0.8. -0.8 current becomes 0. So according to Millikan say that this called stopping potential. That means whatever kinetic energy possessed by the electron, all is equal to the work done by the electric field. Okay. So work done by the electric field is this stopping potential multiplied by the charge. Okay. Is the kinetic energy of the electron at that moment. So EVS, kinetic energy. So we go back to the slide. Go back to the slide. Okay, now see this formula, the HF, work function, kinetic energy, right? The kinetic energy, Millikan said, can be replaced with EV0, EV0 or EVS. V0 means called stopping potential. The minimum potential required to get get zero photocurrent, zero photocurrent. Okay, the minimum voltage. This is the kinetic energy. Okay, now the equation HF, right? The HF So it tend to become like this. Okay, let me go to the whiteboard to explain. Okay, so HF equals to work function plus kinetic. Einstein stuck with kinetic. So now Millikan said, okay, it's EV naught. Let's say I put normal EV naught stopping potential. Okay, according to Millikan now, if Einstein is correct, now you want to conduct an experiment. He changed the frequency of the source. Okay, so you got different frequency. So what it does, you go and change this. How to change frequency? You change the light color from violet. We got the just now I think for violet we got 0.8 stops. Then it changed to blue. It changed to blue. You get the new stopping potential. It's got the new stopping potential. So you get the stopping potential. Okay, got the data. Then he predicted. He predicted if Einstein correct. If Einstein is correct, if if a graph frequency versus kinetic energy. Okay, so V naught later can use to calculate the kinetic energy one. V naught, you should get a straight line like this. It must. If Millikan got a straight line, that means Einstein is correct. Okay, but Millikan really expected it's not a straight line. He thought it's wrong. Okay, but when he conduct the experiment, it looks like you got a perfect straight line. Okay, you got a perfect straight line. So the first time Millikan, when he do the experiment, he found that the graph plotted. This is the graph plotted. The stopping. Oh, this is sorry. This is yeah. This is frequency versus stopping potential. Kinetic energy, stopping potential. Kinetic energy also can. Many versions. So here you plot stopping potential. If stopping potential means, is it going to be a straight line? Stopping potential versus frequency. Okay, we don't go kinetic. So this is frequency versus kinetic. Sorry, I made a mistake. According to the slide, they put stopping potential versus frequency. Do you get a straight line from linear law? Use this. So V naught is what? Negative work function plus HF, right? Okay. Yeah, negative work function plus HF. Okay. So EV naught lah, EV naught. Okay, EV naught is HF minus work function. So V naught is what? HF over E minus work function over E. Yeah. Is it a straight line? Is it portraying a straight line? Y equals to mx plus c. Y is your work function. X is what? X is your frequency, right? Frequency is your X. Yeah, your gradient should get what? H over E. Your C is what? Negative phi over E. Phi, work function, E, H, all are constants, you know. So therefore, it should be a straight line. So V naught versus F also must get a straight line. Theoretically predicted, but in experiment also they got a straight line. You got a straight line. Okay. But Millikan still not happy. Okay. He's still not happy. So he got a straight line. And the gradient, according to this graph, the gradient is found to be what? The gradient is H over E. H over E. The gradient is H over E. Okay. So Millikan said, okay, still more tests to be done. So he said, okay, let's we try with another experiment. Okay. Another experiment. We change the metal plate. We change the metal plate. How this graph should going to look like? Guys, come on, predict. Okay, let's say the first metal plate you use, it has a certain work function. Okay, let's say smaller work function lah. The phi, let's say, is 10. Okay. Now let's say the Millikan, if he repeated with another metal plate with a greater work function, how this graph going to look like? Greater work function. What going to change in this formula? Is it the gradient going to change or the y-intercept going to change? What going to change? Anybody? What going to change? we use another metal plate with as a greater work function. Gradient change or y-intercept change? Yeah, good. Class is good. So y-intercept will change, right? Right? You see this formula? The work function is at the back one. Is this your y-intercept one? So y-intercept should change. Is it gradient will change? Gradient should not change. So Millikan know that. Okay, let's see. We choose a different metal plate. We conduct this experiment again. We see, do we get a straight line, but with a different y-intercept? When you do the experiment, he found the same thing happens. He got a straight line with the same gradient, but the y-intercept changed. Okay, the gradient was exactly same as the first line. So finally concluded. So Millikan proved that Einstein's theory is correct to explain photoelectric effect. So the light do behave. The energy of a light is looks like is in a packet. It's in a packet. So after this is proven, so after 1918, I think Millikan did this experiment. 1921, Einstein awarded with the Nobel Prize for photoelectric effect. Important solution solved by Einstein with help of Millikan. With help of Millikan. Okay, guys. So yeah, so time's up. We'll be continuing this tomorrow. We'll be continuing this tomorrow. Try to read back the videos and everything. Try to understand the concept. Okay, the concept is very theoretical. Okay, you never heard this before. Very theoretical. Maybe you feel a little tough for you, but just trust me. For your seniors also, when you go for one round for quantum, they feel a little challenging. But once they understand the concept, I think quantum is one of the easiest question you can do. Okay, trust me. Okay, Nicholas, any questions? We are still photoelectric effect. The next class also we go finish the photoelectric effect. Just a little about photoelectric effect. Go and read these slides explanation. Try to conclude something work function. Indirectly, I already taught this all. Okay, you just read through. The next class, we just make a conclusion about photoelectric effect. Any questions? No questions. Okay then, I see you back tomorrow. Thanks.
Thanks, teacher.